Hi guys, welcome to Chemistry Laytonville High School 2020. I was really hoping to not have to do these videos this year, but I still have to, and they are just as amateurish as before, but I have way less time to edit, so you're going to have to put up with what I have, and hopefully it'll be okay. Let me know if it's not, and I can try on the next video to adjust, but I can't do this one twice. Right now we're working on the nucleus in chemistry, and I want to supplement some of the things that are in the edgenuity lesson. I feel like they went over them very quickly, and I think we need a little bit more background for some of those things. In particular, the strong nuclear force. So I've got a diagram here. The objective today is students will be able to explain what binds positively charged protons in the nucleus. And that means you are going to have to explain. So I'm going to explain as best I can. You need to listen to my explanation, watch the edgenuity lesson, and then be able to explain yourself. Why are they there in the first place? So to start my explanation, I'm going to ask the question, why not? Why shouldn't we be able to stick positively charged protons together in the nucleus? And to start with that, we're going to talk about magnets, which actually are more like protons than you would imagine as you get deeper into the subject. But as we stick two magnets together, I'm sure you guys have seen this, when you stick two magnets together, they want to go together, right? They fit together, and it's hard to pull them apart. If I get two ordinary kitchen magnets, though, and I flip it, and then I try to stick it together, all of a sudden they don't want to go. Like if I try to press it, it presses away instantly, and it wants to flip back over and go the other way. That's because I'm trying to stick the two poles that are the same together. And they don't want to go together. The two positively charged poles don't want to go together. If I stick positive and negative together, then they go together just fine. The same is true in electrostatics. If I have a positively charged proton and I try to stick a positively charged proton near it, it doesn't want to go. And you'll see here repulsion on the graph. That's because as I get closer, it's going to want to repel more and more. But notice this is actually a very small slope. And the reason is that once they get close enough, which is very, very close, right? The atoms are very small. Once they are very, very close, suddenly the proton is very happy, right next to the other proton, and it'll sit right in that spot. If you try to push it closer, it doesn't want to go. If you try to pull it further away, it doesn't want to go. Okay? As long as it's in that spot, it's very, very stable. And that is the basics of all the matter that you see around us. Every single piece of matter that you can see or hear or out in space is following this rule. That is, these protons, as they move close together, are very happy in that space. Do they ever get closer? Yes, they do in a supernova, in a neutron star. These things get very closer together than they like to be, and that's partly why we have supernova and black holes, is we try to put these closer together and they just won't go. So, but in normal matter that you can see, this is where they are. The proton comes close, it falls into this nice little well, and it stays very close to the other proton, which forms the atom, right? When you stick more than one proton together. Remember, one proton is hydrogen, two protons are helium, and you can check that on the periodic table in your book. Okay, so what holds this proton here? Now, physicists these days will tell you it is the strong nuclear force. And you hear that all the time on TV and, you know, in the newspapers. And I suppose it's a force, but honestly, it's a force made up to describe an observation. The observation is that this is where the protons like to be. And we make up a force that explains why they like to be there. But the reality, what we know, is that this is where a proton is stable. And that's it. Quantum mechanics and nuclear physics, the whole field is trying to figure out right now in a unified theory why protons like to be there. And the question is still out. But the word we use for it is the strong nuclear force. And that strong nuclear force is in opposition to the electrostatic force. that is the force that pushes these apart, the repulsion that pushes a positive charge away from another positive charge. So the strong nuclear force opposes the repulsion easily in this spot only. You get further away and suddenly that repulsive force takes over and whee, the proton flies away. Okay. Oh yeah. In the video, they do give the explanation, the modern explanation of why the proton likes to sit here. And it's a particle physicist's explanation. And what they say is, well, mesons fly from one proton to the other, and that's what holds them there. But it doesn't really explain, well, why can't the mesons fly when they're closer together? And why can't they fly when they're further away? And the reason for that is, in a particle physics explanation, is imagine you and your friend each have a ball. And you can only throw the ball once a second, exactly on the second. No, let's do it once every 5 seconds. No, better be once a second. And you can only throw the ball once a second. So like throw, throw, throw. And you have to keep that going in an equilibrium. I'm sure those of you who play basketball will realize that there is only one distance at which you can both throw the ball and catch it and still continue the game. If you get further away, the ball won't reach you until too late and you'll get behind. If you get too close together, the ball's hitting you in the face before you've thrown yours. And so that's what it is with the mesons. They have to go back and forth in this clockwork fashion, and that can only happen at a single distance. And that's all I'm going to say about that. The mass deficit that they talk about in the video, as you push a proton towards here, it doesn't want to go. And then all of a sudden, it's very happy there. Okay, so it's going from an unstable position to a very stable position. And whenever that happens, energy is released. So when we push a proton together to another proton, we release energy. That's what's happening in our sun right now. Hydrogen atoms are fusing, undergoing nuclear fusion to helium atoms. So hydrogen is going to helium, and I'm not going to balance the equations, and it releases energy. Okay, so where does that energy come from? And that's where they talk about the mass deficit. When this proton falls in here and releases the energy that released is equal to a lost mass, because two protons together actually have less mass than two protons separated. Crazy, huh? Okay, so this mass that gets lost gets turned into energy, and in the lesson you learn how to figure that out. Like how much mass is that, and given how much mass, how much energy is released. And this is the energy that reaches us from the sun every day, came from mass inside the sun. I think about 10,000 years ago, because it takes 10,000 years for the energy from fusion in the center of the sun to get all the way out to the edge of the sun and then reach us. Okay, you know what, I'm take that back. It's not 10,000 years, and I think it might be 1 million. Sorry guys, I forgot right now. You can look it up. Fusion also occurs in nuclear weapons. Remind me to show you the picture of Bikini Atoll, which is one of the pictures of a fusion weapon, the first fusion weapons demonstrated on Earth. It is awe-inspiring, and I can't show it right here. Now for the fun part. Okay, so maybe some of you know about the orange plate. I'm gonna bring it over here, and then I'm gonna stand over here. I hope you guys can see the orange plate in the video. Now, you notice there's this ideal nucleus size, right? What happens when our nucleus gets bigger? What happens when we stick too many protons and neutrons together? Neutrons, by the way, help keep those protons at that perfect distance. That's partly why neutrons are in the nucleus, is to hold it in just the right shape to be this exact size. So when you stick too many things in there, where'd my pen go? Let's say I stick too many protons and neutrons in there, and it's starting to get too big. It's like your sock drawer after you do laundry, and it's just like way too many. What happens? And that's what I'm going to show you now. I have a Geiger counter. I'm gonna turn it on. This Geiger counter clicks. Oh wait, it's not going here. Hold on. Get going. There we go. Okay, the Geiger counter's on. You hear it? It's a little bit loud. Let me, just a second. Here. Okay, so this is actually a little high, and you'll see why in just a moment. Can you see that? That plate has the element uranium in it, and it's radioactive. Find uranium on the periodic table. It's really big. I think it has atomic number 98, and I'm sorry I don't always remember them. But it's big, and so it's too big, and so pieces start to fly off of it. And that's what radioactivity is. And that's pieces of atoms flying off, splitting it. That's why uranium makes such a terrible weapon, because it's easy to split and to make an atom bomb. So remember, some radiation goes through things like plates and wood and skin, like x-rays. So I always wanted to see what kind, uh-oh. That's not good. It should not be coming through the plastic. Okay. So I'll be designing a better container for our plate for next time. Anyway, thanks, and have a great day.